Hi everyone, I am Bruno Pasqualotto Cavalar, and I'm talking about Monotone Circuit Lower Bounds from robust sunflowers. This is a joint work with Mrinal, Kumar, and Benjamin Rossman. So in Boolean circuit complexity, we're interested in the computational model of Boolean circuits. And here we're interested in a Boolean function, and we want to know what is the size of the smallest circuit that computes the function. This computational model is in some sense complete, in that every algorithm can efficiently be represented by a Boolean circuit. And we want to prove lower bounds for the size of circuits that compute explicit functions. However, proving superlinear unconditional lower bounds for circuit size is still open. We know that almost every Boolean function requires exponential Boolean circuit size, but we haven't been able to prove a superlinear lower bound for an explicit function. So that motivates monotone circuit complexity. We're interested in whether restricting the circuit in some way helps us to prove lower bounds. So given two Boolean strings x and y, we say that x is at most y if xi is at most yi for each index I. And f is monotone if it respects this ordering. So if x is at most I, then f of x is at most f of y. And a monotone circuit, it's a circuit without negations. It's a circuit that allows only OR and AND gates. And it's not hard to see that monotone circuits compute only monotone Boolean functions. And every monotone Boolean function can be computed by a monotone circuit. One of the most important examples of monotone Boolean functions is the k-click function. So given a graph represented by its adjacency matrix as a binary string, the k-click function outputs 1 if the graph contains a click on k vertices. It's not hard to see that k-click has a monotone circuit, can be computed by a monotone circuit of size n to the big O of k. Simply by doing brute force. You try for every set of k vertices if there's a click in this set. And k-click is of course a monotone function because if a graph contains a click and you increase edges in the graph, it will continue to have a click. So motivations for studying monotone circuit complexity is that it is one of the largest circuit classes for which we have strong unconditional lower bounds. It has many connections to other measures of complexity, such as proof complexity, communication complexity, and optimization. And there are many mysteries and open questions yet for monotone circuits. So a brief history of monotone circuit lower bounds. So in the early 80s, the best lower bounds we had for monotone circuits were linear lower bounds. So Rasberov came and he proved the superpolynomial lower bound for the k-click function. But to do that, he introduced the approximation method. After Rasberov, people applied his technique to give even exponential lower bound for a monotone Boolean function. And this line of work culminated in 1987 by a work of Andrew Eve, who gave an exponential lower bound in n to the 1/3. And in the 2000s, Harnack and Raz also gave a lower bound of exponential in n to the 1/3 for a monotone Boolean function. But ever since these early works, no improvement on the order of growth of the exponential function had been given. And we proved the first monotone circular bound, that is exponential in n to the 1/2. And this lower bound of ours depends crucially on the improved robust sunflower bounds that were obtained recently by Wizlovit Wenzang and Anup Rao. And truly exponential lower bounds of the form, exponential in linear in n, for monotone formulas, which are monotone circuits with a tree-like shape, were obtained only recently by Pitassi and Robert. And for the click function, the first lower bound that was given was, as we saw, by Rasberov, and he proved an n to the omega of k lower bound when k is at most log n. And then Alon Bopana proved n to the omega of square root of k lower bound for the k-click function when k is at most n to the 2/3. So this gave an exponential lower bound for the click problem, because you can take k to be not only log n but even up to n to the 2/3. But the lower bound was not tight, in the sense that the best upper bound that we have for monotone circuits, as we briefly mentioned, is n to the big O of k. And Alan and Penna used the approximation method as well, and they used a variant of sunflowers, which we call like lopsided sunflowers. In our work, we were able to prove tight lower bounds for k-click when k is also large. So it's when k is almost up to n to the 1/3. So it was the first tight lower bound for k-click when k is large, and our work avoid the n to the big O of square root of k barrier of Krychek and Oliveira. They showed that if one wants to prove a lower bound for k-click that's tight, you would have to else avoid the approximation method altogether, or to consider a different pair of distributions. We're able to use the approximation method, but we use a different pair of distributions, and we were able to do that by introducing another notion of click sunflowers, which we'll review later. So how does the approximation method or Rasburov works? So given a circuit C, you want to define for every gate end an approximate end gate, and for the gate R an approximate R, and for every gate you change the end gates for approximate end gates and R gates for approximate R gates, and you want to show that this approximate circuit C tilde approximates the original circuit with high probability if the circuit is small, if it doesn't have many gates. And we do that by the gate-by-gate union bound. We just count how many approximation errors we make every time we change a gate for its approximate version. And if the circuit is small, then the total amount of errors is small, so the approximation is good. But what we also want to show that every approximator makes a lot of mistakes with respect to the original target function for which we are trying to prove a lower bound. And this implies that the monotone circuit complexity of the function is large. Okay, otherwise we would be able to find an approximator that makes a lot of mistakes when approximating the function, but is also very similar to a circuit computing the function, which is a contradiction. So how to find such approximators? So Rasburov did that by considering the sunflower lemma of Erdős and Rado. So a sunflower is just a set system where every set they all intersect at the same part, and they are all disjoint outside of this set. And Erdős and Rado proved that every large enough set family contains a sunflower. And so this gives a bound to the number of mean terms of approximator by this procedure, which is called the blocking procedure. So if a function contains too many mean terms, you can just block, take out all the petals, and put the core of the sunflower that is in the set of mean terms. And you can show that there aren't many, that you don't make many approximation mistakes by this procedure. So this gives a bound to the number of mean terms of approximator from the sunflower lemma. And by using variance of sunflowers, so if you have a structure that looks like a sunflower but it's not really a sunflower, you're able to obtain even better parameters than those that are given by sunflowers. This leads to better approximation bounds, which in the end translate to better monotone circuit lower bounds. So what's precisely a sunflower? So a sunflower is a set system such that every two sets intersect at the common intersection of the family, and they are all disjoint outside of this family, outside of the core, I'm sorry. And Erdős rather proved that if L is a non-uniform set system and F is this large, then F contains a sunflower with R petals or R sets. And robust sunflowers. So what are robust sunflowers? So you can think of set system as a hypergraph as well. And we say that this hypergraph is a p-epsilon robust sunflower if when you take p-bias subset of the verses and you unite it with the common intersection of all the edges of the hypergraph, then the union of these two sets of vertices will be independent in the hypergraph with probability at most epsilon. Or equivalently, the p-bias subset W together with the core Y will contain an edge of the hypergraph with probability larger than 1 minus epsilon. Equivalently, we're saying that this DNF, which is formed by the first taking the conjunction for every set of the family of the literals that correspond to elements of the set, and then an union over all the sets of the family. If this DNF is satisfied with high probability, when you take a p-biased input and you restrict the variables of y to be equal to 1. So that's a p-epsilon robust sunflower. And the first robust sunflower bound was given by Rossman when he introduced the concept, and he showed that if the family is this large, then it will contain a p-epsilon robust sunflower. And recently this bound was improved by Always Love It Wenzon, and they show that if it's this large, the family also contains a p-epsilon robust sunflower. This gives a significant improvement on the sunflower conjecture. In other words, this gives bounds also to the size of families that do not contain a sunflower. You can do that by showing that every robust sunflower with the right parameters also contains a sunflower. And Always Love It Wenzon proved that their bound is basically tight when n is omega of L log L. You can see that in their bound there's a big O of L there, and Rao gave an improvement on the bound of Always Love It Wenzon. In particular, he showed a lower bound where this big O of L is just 1 times L. And this improvement is crucial for our monotone circuit lower bound. It's because of his bound we're able to get this nearly exponential in square root of n monotone circuit lower bound. And click sunflowers. So in all those other bounds for robust sunflowers, we don't care about what shape the sets of the family have, but it's possible to give better bounds if we assume that the sets have a certain shape. So precisely what we mean is the following. So let Gn denote all the graphs G with n verses. This is equivalent to the power set of all the pairs of verses of the graph. And for every subset of the verses, we let Ka denote the graph on n verses that has a click on A and no other edges. We call this graph a planted click. Let KL denote all the planted clicks where the click size is L, and K denote all the planted clicks. And we say that a family of graphs on n verses is a p-epsilon click sunflower if F is itself a p-epsilon robust sunflower, and all the sets, all the graphs of the family are planted clicks. And the theorem that we showed is that if the family is made of planted clicks where the clicks have L verses, and the family is this large, then it contains a p-epsilon click sunflower. What I have to note here is that if we apply the robust sunflower lemma as in a black box way, we would get a L choose 2 exponent in these places that we have L, and this is worse than what we were able to prove, and not having this L2's 2 in the exponent is crucial for our n to the omega k lower bound for large k. And the proof of this theorem is similar to Rossman's original bound for Rossman sunflowers by using Janssen's inequality. So further questions? It will be very interesting to finally obtain truly exponential lower bounds for monotone circuits. Indeed, better robust sunflower bounds in the regime when L is omega of n imply truly exponential lower bounds. We didn't discuss that in the paper, but in a few months later, I wrote this in more detail in my master's thesis, and this is not ruled out by Awe, Lovett, Wu, and Zhang lower bound, because the lower bound only holds when n is omega of L log L. So perhaps very robust sunflower bounds are indeed possible when L is very large. And indeed, in our work, we show a truly exponential lower bound for monotone arithmetic circuits computing a general class of polynomials. This does not translate to monotone Boolean circuit lower bound, but it does give some hope that this may be possible as well in the Boolean setting. And when we analyzed the click sunflowers that we introduced, we only used the Janssen's inequality, the technique that was first introduced by Ben Rossman. We didn't use these new techniques for analyzing robust sunflowers. So perhaps it's possible to give better bounds for click sunflowers, which would in the end translate in Taylor bounds for k-click for an even larger range of k. That's it. Thanks for listening.